Hello, everybody. We got more on optimization. So, this one is about making a box out of a certain amount of material. So, here it says 1,200 square centimeters of material is available to make a box with a square base and open top. Find the largest possible volume of the box. Okay. So, the thing that we're trying to optimize is volume. Okay. This is what we want to maximize. Always think of optimization problems like this. There's something to maximize or minimize, and then there's a constraint. So, what's our constraint? Our constraint is the amount of material that we have to work with. Okay, this is our constraint. Okay, so centimeters squared. Centimeters squared is literally centimeter times centimeter. Okay, so this is an area. So like what I'm saying is this is like this is kind of like 1 square centimeter. If each one of these sides is a centimeter, then this is a square centimeter, and we have 1,200 of these to work with. Okay, so box has 6 faces, but it's got an open top, so -1 for the open top. That's a total of 5 faces. Okay, so that's the first thing to understand is we're going to have a total of 5 faces to work with. And then what does each face look like? Okay, so the box has a square base. Okay, so that means that if you're looking at it from above, then this is going to be a square base. If this is x, then this is going to be x as well. Okay, now it doesn't necessarily say that the height of the box has to be the same as the length or width, and so the other view would be kind of like this. Um, so like if this is x, then the height is something different. The height is y. Okay, and there's one of these. This is the bottom. And this is each of the sides. So there's going to be a total of 4 of these. Okay, so let's write down the total surface area of the box because that's what the constraint is. This is about the surface area. Surface area. Because this is the total surface area that we have to work with. And so we know that this surface area is going to be distributed between the different faces of the box. Okay, so surface area. Conceptually, it's going to be the area of face 1 plus face 2 plus so on up to face 5. Okay, so 3, 4 are not shown, but they're understood to be in there. Okay, so face 1, let's say face 1 is the bottom. So the area of face 1 is going to be just x times x. X squared plus, and then the other 4 faces are this one. Okay, so that's going to be xy plus xy plus xy plus xy. Okay. See, I guess I can try and draw the whole thing. I mean, I think you all can. I'm sure you can visualize it without this, and maybe it'll be entertaining for you to watch me fail in drawing a three-dimensional box here. We can try. There's that one. There we go. There we go. There we go. So this is kind of like if we turn it on its side. So it'd be like this is X, and then this is Y. So we have like Y here, Y here, Y here, Y here, so on and so forth. That's actually not too bad. So anyway, so let's do this. This is going to be x squared plus 4xy. And we know that this has to be equal to the constraint, which was 1200. Okay, and just like we've done in previous optimization problems, the purpose of the constraint is to write y in terms of x, basically. One variable in terms of the other. So I'm going to solve this thing for y. If possible, yes, okay. I want to subtract x squared from both sides and then divide by 4x. Okay, so I'm going to have 4xy equals 1200 minus x squared. Subtract x squared from both sides. And then divide both sides by 4x. Okay, and so then we get y equals 1200 minus x squared over 4x. And there's y in terms of x. So now, volume, right? The volume is the thing that we are trying to maximize. And so if we just look at this little three-dimensional guide that I made here, the volume is just going to be, length, width, height, right? X, X, Y. So the volume will be X times Y, which is X squared times Y, which is X squared, and then Y is this. Y is 1200 minus X squared over 4x. Okay, and so we can do a little bit of algebra. We're going to have an x that's going to cancel. So that's going to give us x multiplied by 1200 minus x squared over 4. I know I'm going to have to take a derivative, so to make this a little bit easier, I'm going to write it this way. Division by 4 is the same thing as multiplication by 1/4. And then if I distribute the x, I get 1200x minus x cubed. And again, that is my volume. Okay, I want to find the maximum volume. So once again, if there's a maximum, the slope at the maximum is 0 or undefined. To the left of the maximum, the slope is positive. To the right of the maximum, the slope is negative. Positive slope, negative slope. Okay, so we want to show that this is the case. So I'm going to take the derivative of volume, so dv dx. The 1/4 is the constant multiple. The derivative of 1200x is 1200 minus 3x squared. I want to set that equal to 0. This is a polynomial, so there's no chance for it to be undefined. Polynomials are continuous on all real numbers. I can multiply both sides by 4 and get 1200 minus 3x squared equals 0, which is the same thing as 1200 equals 3x squared. Divide both sides by 3, and I get x squared equals 400. So x equals plus or minus 20. We're going to reject the negative 20 because it's an impossible length. Length is strictly positive. So then x equals 20. We want to show that x equals 20 is max. We have to show that that's the case. Okay, so the minimum value of any side is, just a number. Just has to be the length, width, and height have to be bigger than 0. So parentheses 0 to 20. and then 20 to, I don't know, infinity. Okay, so if I pick a number here, pick like 1. If I pick a number here, pick like 21. And I want to show that the derivative, what I'm trying to show is that the derivative at 1, before I do the math, I'm trying to show that this one is positive. Yeah, positive, and that this one's negative. That's what I want for a maximum. Let's see if it's the case. Okay, so v prime at 20, not v prime at 20, v prime at 1. How about that? I didn't mean to write 20 there. V prime at 1. That's to the left of 20. I want the slope to be positive to the left of 20. So 1/4 is positive. 1200 minus 3 times 1 squared. 1200 minus 3, definitely positive. Definitely bigger than 0. Okay. So that's good. And if I plug in, say, 21, then I want the opposite to be true. So let's plug in v prime at 21. That's going to give me 1/4 multiplied by 1200 minus 21. 21's, oh man, 21 squared. Oh boy. Okay. Let me figure that one out. Let's see. 21 squared. Boom. Times 3. 1323. Okay, so this is clearly a negative number, which is less than 0. Okay, so slope goes from positive to negative. That means, therefore, we have a max at x equals 20. And there we go. So if x equals 20, we need the volume. Okay, we've verified that x equals 20 is the max. So our volume is right here. Here's v. Okay, so the volume is going to be 1/4 multiplied by 1200 times, and then x is 20. That's the maximum. 1200 times 20 minus 20 cubed. Oh boy, 20 cubed. 8,000? Yeah. 24,000 minus 8,000, 16,000. So yeah, volume 16,000. Where was I? I thought I was writing somewhere. Where did it go? X equals 20. Yeah, here we were. Right here. 1/4 times 16,000, which is 4,000 cubic centimeters. Centimeter times centimeter times centimeter. Yep, awesome. There we go. There's the maximum volume. Another optimization problem. I would say a problem like this would be likely to appear if they are going to choose an optimization problem. I feel like this would be a good one. The question is will they put an optimization problem on there or not? I'm not sure. Anyway, that's it for that problem.